Alright, here's lab one, electric charge and floating tape. The purpose of this lab is to investigate how insulating materials acquire electric charge and observe electrostatic repulsion between two charge tapes. We need to measure floating equilibrium distance and use Coulomb's law to estimate the charge on the tape. Then compare the experimental measurements with the computational modeling. And these are the measurements of the tape, which was 2.2 meters. Tape mass was about a gram. Well, no, about 0.0002 kilograms. And the floating distance was 0.04 meters. The system was a top tape, surrounding was gravity and electric repulsion from the bottom tape. The forces on the tape were gravity and electric force. And the equations for these are right here. Calculations. These are the equations I use to get the electric force and fields, and also account for the excess electrons. In Model 1, the assumption was that each tape behaves like a single point charge at the center. And this is the coding I did for it. Some of the strengths were that the method was simple and matches the experimental calculations, while some of the limitations were it ignores charge distribution, ignores tape geometry, and treats tape as a single point. Model 2, the assumption was that each tape is in line of 10 small charges, DQs, with a uniform distribution. The model computes electric field at each DQ and net at each Q, net electric force on the top tape, and in comparison to gravity. This model is better because it accounts for distributed charge, includes varying distances between DQs, and captures edge effects. It produces more realistic electric field geometry. Discussion. Assumption for both models is the tape is rigid in 1D, charge is uniformly distributed, no charge migration, and ignores tape thickness, wrinkles, humidity, and airflow. Some possible sources of error are tape mass estimate, human error measuring floating distance, non-uniform real world charge distribution, error currents and tape twisting, and VPython ignores internal interactions within each tape. What ifs? If the electrons were positive and protons were negative, all electric forces reverse direction. Like charges still repel, unlike charges attract. Tape behavior stays the same. And Coulomb's law depends on a relative sign, not particle identity. And as for the conclusion, these are the final values for everything. And the line charge model provides the most realistic estimate of the tape's charge because it accounts for the distributed nature of the charge and the geometry of the tape. Both experiment and simulation agree closely, validating the equilibrium method.